I am Barry, and today I'm going to talk about the introduction for our IF assignment. And in the field of the digital electronics, filter will play an important role, which is used to filter out the unwanted signal and retain the quality of the signal. And there are four types of filter. First, low-pass filter is a filter that allows frequency lower than the cut-off frequency, but reject the others. And this is the circuit for the low pass and the graph for the low pass filter. And second, the high pass filter is a filter that filter out the frequency which is lower than cutoff frequency, but accept the frequency that higher than the cutoff frequency. And the high pass filter will work opposite of the low pass filter. And this is the circuit for the high pass filter, and this is the graph for high pass filter. And the third filter is a band pass filter, consists of two cutoff frequency, which will filter out the frequency not within the range, but accept the frequency in the range. And this is the circuit and graph of band pass. And the last type of the filter is band stop filter. It also consists of two cutoff frequency which reject the cross frequency within the band but accept the frequency of the band. And this is the circuit and graph for band stop. And the microwave filters are the electronic filter that will operate on the signal between megahertz and gigahertz. Microwave filters plays an important role in any RF front end for suppression of our band signals, and it typically consists of two types of filter design. The first one is lump design. Design consists of resistor, capacitor, and inductors, and it provides good compact but low performance. And the second, the design will be distributed design, and design consists of stump, couple lines, and cascade lines. It provides a better performance. And there are two types to design the microwave filters. The first is image parameters method, which design K filter, M drive filter, and composite filter. And the second method is insertion loss method, which design a maximally flat response filter and equal ripple response filter. And that's all. Thank you.
Hi, my name is John Richard. So I will talk about theory now. So we have three main theory here. First one will be the pie filter design. So what is a pie filter design used for? It's good for high frequency noise rejection. It's effectively reject high frequency noise. If I have a better impedance matching, they have a improved impedance matching. It's also very simple and efficient because it only consists of a series of inductor and two shunt capacitors. There's no extra components that is very expensive or anything. So next, it's very variable and tunable. It's easily adjustable for a different frequency band. So it's very useful in a power supply RF circuits. It also have it's also able to reduce voltage ripple. It efficiently remove voltage ripples in a power supply, enhancing a DC output stability. And lastly, it have a wide application that for good for improvement and interference elimination. So next theory that we'll be using is Richards transformation. So what is the use? It's good for conversion of lump parameter. It basically transforms inductors and capacitor into transmission line lengths. It's also good for a high frequency application. So it's useful for component dimension, matches the wavelengths. Also, used for frequency characteristics maintenance. It keeps the impedance of frequency characteristic of a lump elements. And lastly, it's good for transmission line implementation because it converts impedance and frequency behavior to the distributed element for use with transmission line. So last theory that they'll be using is Kuroda identities. It basically helps the Richards transformation. It enhances it. It provides mathematical transformation for easy implementation of distributed element filter. It also simplifies filtered networks because it transforms the complex network into more workable configuration using transmission lines. The Kuroda identities improve visibility and manufacturability. It makes filter designs more practical and manufacturable, especially in the microwave filters. It four primary identities. It used the primary identity used to transform the impedance or admittance, its scale impedance, and invert network element. Another function is the stub conversion. It converts series inductive stubs into shunt capacity stub and vice versa, aiding a filter arrangement. Lastly, it improves impedance matching. It helps enhance impedance matching and reduce reflection in wave propagation. And that's all. I will give it to my friend for the calculation, the realization.
Hi guys, now let's talk about the chapter 3 for our assignment. So for the chapter 3, we have the low pass filter. So for the low pass filter, there are two types of design, which are the lump design and the distributed design. So let's take a look at the lump design first. So by using the given information, we can find that the value of omega divided by omega c minus 1 is equal to 1.581, and then the insertion loss, which is the attenuation, is 30 dB. So by looking at the graph of attenuation against normalized frequency for 0.5 dB ripples, we can find that the value of n is equal to 4. So by looking at the elements value for 0.5 dB ripple, so since we get the value of n is equal to 4, therefore we can get all the value of G1 until G5, and then we list it down here. So since we're using the pi network, therefore there will be 3 capacitors and 2 inductors. And then by using the formulas, then we can get all these values. So for all these values, if you plot it using the software, you can get the low pass filter successfully. Next, let's talk about the distributed design. Without using any formulas or calculations as before, we can use it. If you wanted to plot it on a PCB, then you need to use the distributed design. So firstly, we get the values of G's, which is here, and then by using the richest formula, then used to transform the individual circuit elements to different transmission line combination, you can see that for the inductor, after it undergoes the richest transformation, it will become like this. And here, there is short circuit, and then for the capacitor, when it undergoes the richest transformation, it will become this, which is the open circuit. If you take a look for the capacitor here, once it transforms into this form, you can see that the formula has been changed. You need to 1 divided by the G. So for the forest, we have 3 capacitors, which are C1, C3, and C5. Therefore, by this, all these 3 values need to divide it, then you can get the value. After you get the value, then you need to plot it. So as you can see, this is the inductors, which is in short circuit, and then these 3 are the capacitor, which is in open circuit. Okay, so next, let's talk about the Kuroda identities. Basically, the Kuroda identities is to rearrange the transmission line. Let's take a look at this first situation, which is these 2 parts. We can see that the Z1 is equal to 1, and then the Z2 is equal to 0.6. By using the formula, we can get that the n squared is equal to 1.6. Later on, we use the Z1 divided by the n2 and the Z2 divided by the n squared. We can get these 2 values. If you take a look at here, this one, which is the inductor, should be the Z1 divided by n squared. Therefore, if you take a look here, you can see that once it undergoes this formula that we have applied, finally, after it transforms, it will become like this. And then for here, we need to calculate it. So therefore, we divide it into 4 parts, as you can see down here. So the Z1 is equal to 0.375, the Z2 is equal to 1, and then same things, we need to find the n squared. But in this case, we're using the different formula for the n squared multiplied by Z1 instead of Z1 divided by n squared. It is because this is in parallel, and then this is in series. Therefore, there are different formulas. And then we applied it, and then you can see all these yellow color highlighted are the answers. Therefore, we transform it, it will become like this. And then if you can take a look at, notice here, for this one is the n squared divided by Z2. So wherever the answer that we get from the n squared Z2, like all these, are the capacitor, which is in parallel. Open circuit. So if you take a look, you can see that all these are the values of the capacitor, which is in open circuit, and then these are the values for the inductor. And then we denormalize it with the 50 ohm impedance for each stop. We can once we multiply it, we can get the final value of it. And then if we want to plot it into the PCB or illustrate in the proper way, you can do it like this. So in this case, this is the input for the RF signal. So once the signal goes in, so it will undergo different lengths and the different ohms and the different length as well. Then this will be the output here. So this is the part for the low pass filter. So let's talk about the band pass filter. So band pass filter is quite similar to what we have learned during the lecture session. So the band pass formula, okay, these all are the given information, and then we find the F1, F2, and the W0, and then we find this little triangle by using the formula. So since the given value of n is equal to 4, then by using the element value for 0.5 dB ripple, we can see that the G1 until G5 will be this, or this with this value. So it has been listed down here. So Later on, we need to convert it. Not convert it, it's like we used to calculate it using the formula, and then we calculate it respectively. Then we can get all the answers.
Hi, my name is Chan Jingming, and I'm gonna do about the ADS software design. And thank you for the calculation that did from Chang Chun Han. We can just directly use the result from there to put inside to the design. So this design is based on using the pi network, which is C1 at here, L2, C3, L4, and C5. And with there is also a 50 impedance, input impedance at here also and here also. So the start, so the frequency is on the result will be start from 1 gigahertz and stop at 12 gigahertz, and the step for each will be 100 kHz. So without further ado, let's run about it. And this will be the looped design result. And we can see the 3.1 gigahertz will be at here, which is the cutoff, and the 8 gigahertz will be at here, which is the initial loss. And we can see it is not very good at the cutoff because it doesn't really match at the negative 3 dB. So the tuning process will be necessary to make it better cutoff frequency. So this will be the result for the looped design. And let's go to the next one, which is the distributed design. So this one will be the distributed design. Wait, okay, here this one will be the distributed design, and from the calculation that given from Chang Chun Han, you can see we can use the calculation to do it at here to find the W and also L. So after we substitute the M sub here, the material subscript to here and fill up the frequency that we want, which is 3.1 gigahertz. And here we change to millimeter. And for the Z naught here is the result that given from Chang Chun Han. And we can just put the number and just put it at here. And this one, if we want to find the front and the back, which is this one, this M lin and this M lin, we just put 90 degrees at here. If we want to find the other rest, we just put 45 degree, and we press this synthesize and we get the W and L. Just copy the W and L in millimeter and put it at here. So what about the MTE ADS? This one, the W1, W2, W3 is based on this, and this. So the W1 will be this one at here. The W2 is at here also. The W3 will be at here. It's same goes to the others. Okay, without further ado, let's start the simulation. And this one is the S parameter as well. So this one is the result before tuning. Okay, let's see about this. We can see the cutoff frequency is not at negative 3 dB, so it is better we can put it at here. So how we do that? We can use based on tuning process. Okay, so this one is the result before tuning. So let's go to the next one. Excuse me, which is the after tuning. So this one is after tuning. This result is after tuning. Basically it's the same one. And let's see the tuning. Yes. Oops. And this one will be the tuning result. Close this one first. And this one will be the tuning results. And this one will be the S21, which is just this one. The result here, you can see when it is 3.1 gigahertz, it is perfectly at negative 2.9, which is negative 3 dB, which is the cutoff. And it is they are insert together the line, so they are crossing to each other. So it means it is the best line for it, for the cutoff. Sorry. And this is the result after tuning, and it is perfectly at negative 3 dBs. Okay, so for the design. Oh, sorry. This one is the tuning that I just did. Yes. Okay. So next we need to put it at the port design, right? So wait for a while. I just opened that. Okay. So firstly, we need to change the input impedance to this one, and we just run it. Windows layout. And this one will be the result that we want. Okay, so next it will be the bandpass filter, and it changes from the capacity for the low pass filter. So low pass filter at here will be C, right? So the C will be changed to the parallel inductor and also capacitor. And for the inductor, you will change to series LC, which is inductor and capacitor, parallel LC, and series LC, parallel LC. So by using the same one, also the input impedance for 50 ohm at here also, and the parameter for the diagram will be start from 1 gigahertz and stop at 6 gigahertz. The step is also 100 gigahertz. So let's run it. Okay, and let's see. So M1 will be at the middle here, M2 will be at here, and M3 will be at here. So this one will be the bandwidth. Okay, that's all from me. Thank you.
So now we're nearing to the end. I will talk about discussion. So the project aim is we reveal the low pass and the band pass filter using lump and distributed element with the ADS software. So calculation and construction, we have calculated the value using various formula and theories, and we construct the circuits. So both the Richards transformation and the Kuroda identities, they were significantly helpful in the project. So for our low pass filter, it required tuning to achieve the desired performance, especially when the range exceeds for 1 or 0 due to the cutoff. So for distributed design optimization, so after tuning, we get the performance that we required, and it was relatively good. As for the bandpass filter, it meets the characteristics and effectively remove undesired frequency. So yes, the simulation results is aligned with the theoretical analysis. So in conclusion, the project successfully demonstrated the design and optimization of a low pass and band pass filter using both a lump and distributed elements. And during the filter design, we have utilized the state-of-art microwave engineering concepts such as Richards transformation and Kuroda identities to realize the requisite filter performance. And that's all from us. Thank you.